So today we are going to continue our discussion on AVL trees. In particular, we are going to look at the insertion and deletion procedure in an AVL tree. So we'll begin with insertion. So we had started this discussion on insertion in the last class also. So suppose I am trying to insert a node V into an AVL tree, right. So actually what I am trying to do is insert a key, right. But so what's the process of insertion in a binary search tree? First you find where the key is, right. You go to that place, you put the key there. Let us say the node in which I put the key is the node in which I put the key is V. Okay. Now this is something we had started the discussion of. So if as a consequence of this insertion it does not remain an AVL tree, then that is because the height balance property is violated. Yeah. And what are the nodes whose heights could change as a result of this insertion, right? Which are the nodes whose heights could change? Recall we defined the height of a node as the height of the subtree rooted at that node. Yeah. So this is this large tree and somewhere below there I insert a particular node. Yeah. So which are the nodes whose heights could change? It could only be the ancestors of this particular node. Yeah, not because it is written here, but you should also understand why it is only ancestors, right? Because it is only in the ancestors of that node whose subtree has changed as a result of this insertion process, right. For any other node its subtree has not changed, it remains the same as before. So the ancestors of this node, their heights might change, and change it will only increase, right, because I have added a particular node. So it is the ancestors of these nodes whose heights might increase as a consequence of this insertion. So if the insertion caused the tree to become imbalanced or unbalanced, then some ancestor of this node V is the culprit, is the place where one or more ancestors, right, where we have a height balance problem. Height balance problem means it will become height imbalance. So height imbalance means one left subtree and right subtree, the difference in heights is more than a 1. So what are we going to do? We are going to essentially travel up the tree from this node V, travel up the tree, which means just keep following the parent pointer, yeah, till we identify the node Z which is unbalanced, right. So I have said it as till we find the first node X whose grandparent is unbalanced, but you can also think of it as I find the node Z whose grandparent which is unbalanced and X is its grandchild. Which grandchild? The grandchild that we went through, the grandchild on the path, right, because a node can have many grandchildren. Yeah, I will show you an example and this would be clearer. And we will call Y the parent of X. So Y is the parent of X and the child of Z then, right. So suppose this was the situation we had, this was an AVL tree, yeah, and I insert, let us say 54 into this tree. So 54 would come here. Why? Because it is larger, smaller, larger, smaller, and so it would come here, right. Now if there is a problem, actually this tree is not height balanced anymore, this is not an AVL tree anymore. So if there is a problem, we said that the problem would be on one of these nodes. So note that these are the only nodes whose heights have changed. Earlier this node had a height of a 0, now it is 1. This node had a height of 1, now it is 2. This node had a height of 2, now it is 3. This node had a height of 3, now it is 4. Which is the first node on this path whose height which is now imbalanced? Is this imbalanced? 50? No, difference of height is 1. This is imbalanced? Yes, right, difference of height is 2. This is 1, this is height 3. Yeah, the height of no other node has changed, the height of this node has not changed. Yeah, so you understand why the heights of only these nodes on this path would change, right. So this node will be Z, yeah, this node will be Z, X would be its grandchild on the path and the parent would be Y.
So X will be the grandchild of the Z1, it is not the element in Z.
Let us call that X is a node, Y is a node and Z is a node. Yeah, so X is the node here. Okay, everyone with me? So we travel up from here, we find the first place where the imbalance happens, let us call that Z, and X is the grandchild of Z. Grandchild means parents, child's child. So child is Y and its child is X. And now we are going to rebalance this tree. So to rebalance this tree, so we are going to in particular rebalance this subtree rooted at Z. And we will do that by performing a rotation, and this is what will happen after the rebalance. This is what the tree would look like. Okay, and what we are going to do today is understand how we came up with this picture. Right. As you can see, I have only changed this subtree. Which subtree? This subtree, the one containing these 6 nodes, 48, 50, 54, 62, 78, 88. They are here, the 6 nodes, but organized in a manner now so that this node is not height imbalanced anymore, and neither is this node height imbalanced. Yes, we are going to understand this process today. Okay, so let us first understand what is a rotation. Right, in the previous slide I used this term rotation. What does rotation mean? So a rotation is a way of locally reorganizing a binary search tree. Okay, so this is part of my binary search tree. This could be a huge tree, I just consider a part of it. Yeah, so U is one node, V is its child, and these are some subtrees. This is the right subtree, this is the subtree rooted at the right child of U, this is the subtree rooted at the right child of V, this is the subtree rooted at the left child of V. This could be a null tree, no node, or could be a huge tree, I do not care. Right. What do I know? Because it is a binary search tree, I know all the keys in T1 are less than the key in V. All the keys in T2 are more than the key in V. Keys in T2 are less than the key in U, and keys in T3 are more than the key in U. Right. This follows from the property of binary search tree. Yes. Okay. Now what is the rotation step going to be? Okay. So first what we are going to do is, let us just forget these links. Okay, let us just look at this, and now this is what a rotation does. Okay. So what has happened? V has become the parent of U. Yeah, you want a replay of this? Okay. So in slow motion, right? So it's sufficiently slow. Okay, that's what a rotation is, and we'll put the links back now. Right? So what happened? What happened was V became a parent of U. The binary search tree property still holds, by the way. Keys of T1 are less than V. Keys of T2 are more than V, so they come here, and they are less than U, so they come to the left of U. Right? So it's still a binary search tree, but we've done some local reorganization. Right? And this will be very useful, we'll see why. Right? So T1 earlier was a to the left of V, it remains to the left of V. Yeah? T3 was to the right of U, if you remember. Let us see. T3 was to the right of U, T1 was to the left of V, T2 was to the right of V. Right? So T3 remains to the right of U, T1 remains to the left of V, but T2 moves from being to the right of V to the left of U. It is now the left child of U. Yeah? Everyone follows this, what a rotation is. Okay. Now let us see how we will use these rotations to do our insertion. Okay. So suppose the insertion happens, so this is the tree, I have not drawn the links, right, but it should be clear what the links are. Who can tell me what the links are? Y is a child of Z, X is a child of Y, these two are children of X, T3 is the right child of Y, and T4 is a right subtree of Z. Yeah. So in the next few slides you will see pictures without these links, but that's just to avoid the clutter. It should be completely clear what the relationships are. Now suppose I did an insertion in T1. Yeah. And these are the X, Y, Z that we encountered in the procedure. So maybe insertion happened somewhere in some leaf, we went up along the path towards the root is maybe somewhere here, yeah, and Z was the first place at which we had an imbalance, and so Y was the child of Z and X was the child of Y on this path that we took. Any questions till this point? Right, I have taken this one picture, but it could also be different, right? Y could have been the right child of Z, yeah, X could have been the left or the right child of Y, right. So there are how many different cases possible? 4. Y could be the left or the right child of Z and X could be the left or the right child of Y. 2 times 2, 4 different cases. So I am looking at one particular case now, that Y is a left child of Z and X is also a left child of Y, and the insertion happened here. So the insertion happened here. So let us say the height of T1, yeah, I am using this to denote the height of the particular thing. The height of T1, let us say originally it was H, and now because of the insertion it becomes H plus 1. Yeah, it cannot increase by more than a 1, right, because after all I am just adding one node. So the increase in height can be at most a 1, and so let us say there was an increase in height. Yeah. So there is an increase in height of this node X also, there is an increase in height of node Y, and there is also an increase in height of node Z, right. That is why Z became imbalanced, right. If there was no increase in height of Y, then Z would not become imbalanced, right. If जो पहले Y की height थी, insertion के बाद अभी भी वही height है, तो Z में कहाँ से imbalance आया होगा? Right? Everything is the same as before. So that means height of Y has also increased, and height of Y has increased because height of X has increased, right? And height of X has increased because height of T1 has increased, and height of T1 let us say has increased from H to H plus 1. What can we say about the height of T2 now?
H minus 1.
What is the height of T2? Okay. So X is balanced even after the insertion, because Z was the first node which was imbalanced. So X was balanced after insertion. So if X was balanced after insertion, अगर इसका height H plus 1 है, so T2 का height या तो H plus 2 होगा, या H plus 1 होगा, या H होगा. H plus 3 नहीं हो सकता T2 का height, क्यों? क्योंकि वहाँ X पर imbalance हो जाएगा नहीं तो, राइट, और ना H से कम हो सकता है. अगर H minus 1 है तो H plus 1 और H minus 1 में 2 का फर्क हो गया. So इसका मतलब X पर ही imbalance हो गया, पर हमने कहा X पर imbalance नहीं हुआ है, Z पे हुआ है सबसे पहले imbalance. ठीक है, everyone with me? So height of T2 is one of these three. Which one? Okay, can it be H plus 2? If it is H plus 2, then originally X is imbalanced, because originally height of T1 was H. If this is H and this is H plus 2, then this was imbalanced even to begin with, but that's not the case, right? Originally it was an AVL tree. So height of T2 cannot be H plus 2. Can it be H plus 1? If it is H plus 1,
then height of X will not be increasing.
Then height of X does not increase, because this is H plus 1, then that means what was the height of X to begin with? H plus 2. And what is the height, if the height of this increased from H to H plus 1, even then its height remains at H plus 2. The fact that the height of X has increased implies that this cannot be H plus 1, because if this was H plus 1, then the height of X did not increase. It remained what it was before, H plus 2. Everyone follows this? Yeah? So this implies height of T2 cannot be H plus 1, so it has to be H. So height of T2 is H. If height of T2 is h and height of this has increased from h to h plus 1, then what about height of x? What was the original height of x? Original height was h plus 1 and now it's become h plus 2. Yes? Is this clear to everyone? So the height of x has increased from h plus 1 to h plus 2. Right? Let us continue this argument. So this is the picture so far. We have argued that the height of T1 has increased from h to h plus 1, the height of T2 is h and the height of x has increased from h plus 1 to h plus 2. What about the height of T3 now?
H plus 1.
Okay, so once again, since y remains balanced, the new height of x is h plus 2. So, and this is balanced, this is height balanced. So, the height of T3 is h plus 3 or h plus 2 or h plus 1, one of these three, because the difference in heights can only be 1. So, it is one of these three. Now, if it is h plus 3, we are repeating the argument roughly. Yeah, if it is h plus 3, then that means y was originally imbalanced, because original height of x was h plus 1. So, y is originally imbalanced. So, height of T3 cannot be h plus 3. If it is h plus 2, then that means that the height of y has not increased, right, because if this was h plus 2, then the height of y, that means originally was h plus 3, right, and abhi bhi wo h plus 3 hi rahegi. So, height of T3 cannot be h plus 2. So, height of T3 has to be h plus 1, right. So, height of T3 is h plus 1. So, if height of T3 is h plus 1, what is the height of y now? So, originally it was h plus 2, because both of these guys were h plus 2, h plus 1. So, this was h plus 2 originally, and now it has become h plus 3. So, it has increased from h plus 2 to h plus 3. Is this clear to everyone? Yeah. Now, what about height of T4? Note that z is imbalanced. Yeah. The new height is h plus 3 of this guy. So, what should the height of T4 be? Or h plus 5?
Initially it was balanced.
Initially it was balanced. So, since z was balanced, z was balanced, so height of T4 is h plus 1 or h plus 2 or h plus 3, right. Since this was originally h plus 2, this could only have been h plus 1, h plus 2 or h plus 3, and since it is now unbalanced, it cannot be h plus 2 or h plus 3, it has to be h plus 1. Yeah. So, this is h plus 1. Who is not following? If you have a question, please ask. Your face will not come on the television, you can ask a question. No? So, height of T4 is h plus 1. Yeah. So, what is the height of z initially?
H plus 3. H plus 3.
This was originally h plus 2, this was h plus 1, so this was h plus 3 originally. Yeah. And now of course its height becomes h plus 4, but now we will do some rotation and stuff like that, so that we will reduce its height. So, its original height was h plus 3. Yeah, everyone follows this. Good. So, we will keep this picture. Right. So, this is what we argued. Let me quickly, this is the final thing we argued, right. These are the heights of the various things. So, when I say from here to here, this, the first thing is what it was originally and what it is now. So, we just need to look at the new values. Okay. Now, we are going to do a rotation around this pair yz. So, what does rotation do? Rotation is going to rotate this, so that y is now going to become the parent of z. Yes? Yeah? Is that clear to everyone? So what do we want to do? We want to move this up so that it will come here and y will become the parent of z. Yeah, and pardon? Yeah, so this is what the rotation is. So let me just draw it here. So y will now become the parent of z. Yes, and where will I put these two? So this is one subtree. This remains as it is. This will not be changed. Yeah. So T3 and T4 are the only ones which have to be. So T4 recalls will remain at the right. T3 will come to the left, and this big piece will remain as it is. Yes, that's what the rotation was. So let's just this is what will happen. Yeah, y has become the parent of z. These two are the children of z, T4 and T3, and this entire thing was to the left. Is this clear? Again, I have not shown the links, but it should be clear what the links are. Yeah, and I have written down the heights. The height of this was h plus 1, this was h, this was h plus 1, this was h plus 1, h plus 1, h plus 1, h plus 1. Yeah, as a rotation, after a rotation, we already saw that the binary search tree properties are maintained. So this is still a binary search tree, but now we want to argue that the height balance property is also restored. यहाँ पे height balance नहीं हो रहा था. कहाँ पे? Where was the height imbalance happening? On z. As you can see, this has height h plus 3, this has height h plus 1. So there is a height imbalance z. Now let's see, what is the height of node x now? Yeah, because this is h plus 1, this is h. What is the height of node z? H plus 2. What is the height of node y? H plus 3. Is everything balanced now? This is balanced. There is only a difference of height of 1. This is balanced, no difference. This is balanced, no difference. Yeah. So we have done a rotation. This is called a single rotation. You will soon see why it is called a single rotation. How much time does this operation take? Just one rotation?
Two operations.
Right. So we just have to do some constant number of operations, right? We have to maybe y we will have to, z will have to become a child of y. So there will be 3 or 4 different reference changes that you have to do, maybe 5, maybe 6, some constant number, independent of the number of nodes in the graph, in the tree. Okay. Now one interesting thing has happened. The original height of z was h plus 3. Yes, that's why we had written this h plus 3 here. After this rotation, the height of this subtree is also h plus 3. Yes. Whatever was the original height of this is the new height of this subtree also. So the height of the subtree remains the same after the rotation. Remains the same as in whatever was the height before the insertion even, h plus 3 was the height before the insertion. Yeah. So after we inserted and did the rotation, the new height also becomes h plus 3. Why is this important?
Because of the remaining 3.
Yeah, because now I don't have to go up further. Yeah, because now any ancestor of this, its height would not change anymore, because I have whatever was the original height of this h plus 3 of this node is the new height of this subtree also. So any of the ancestors of z, their heights would become the same as before, and so there will be no imbalance on them, right. So as I am marching up, after I did my insertion, as I started moving up, I find the first place where there was an imbalance, I did the rotation, yeah, and I am done. I don't have to go up any further.
But is this going to hold always?
Let's see. So we have actually considered only one case, one out of 4 different cases. Yes. Why one case? Because we said y is a left child of z and x is a left child of y. Now there is one symmetric case which is a symmetric, both are right, that I am not going to handle because I trust all of you can believe me there that it is a symmetric case completely, right. So the other case is this one, yeah, where x is, let us say, a right child of y which is a left child of z. Okay, this has a symmetric case which is that y is a right child of z and x is a left child of y. Again, that is completely symmetric and we will not handle that. Okay. Okay, so let us repeat the argument that we had. So once again I am assuming that the insertion happens here, right. It could happen in any one of these, but again it's symmetric. Let us assume it happens here. So this height went from h to h plus 1. What about the height of this guy, right? So since this is balanced even after the insertion, the new height, so the height of this is either h plus 2 or h plus 1 or h. If it is h plus 2, then that means x was originally imbalanced. If it is h plus 1, then that means that the height of x is not changed. So it has to be h. Yeah, I am repeating the arguments, it is the same as before. Yeah, so if this is h and the new height is h plus 1, so what is the new height of x? H plus 2, and what was the original height? H plus 1. So its height moved from h plus 1 to h plus 2. Now let us look at the height of T1. Well, since y is still balanced, then that means that the height of T1 is either h plus 3 or h plus 2 or h plus 1, right. Now if it is h plus 3, then that means y was originally not balanced. If it was h plus 2, then y's height has not increased, so it has to be h plus 1, which means y's height has increased from h plus 2 to h plus 3, which means that now since z is imbalanced, the height of T4 has to be h plus 1, yeah? Which implies that z's original height was h plus 3, yeah, exactly the same as before, we have not made any difference, yeah. Okay, but now the rotations will have to be different a bit. Okay, which of these three keys, so in x, y and z, which of these three keys is the middle key? X, y or z, which of these is middle? X, z is the largest, y is the smallest, right. So if you recall, in the previous rotation we had x, y and z again there. In the previous rotation, which was the middle key? Y, because they were all in a line, yeah. So z was the top, y was its left child, so which means z, y is less than z, and x was its left child, so x is less than y is less than z. So after the rotation we ended up making y the root, the middle child, the middle key we ended up making the root. Here also we would want to do something similar, but except that the middle key is now x. Okay, so we are going to do a two-step rotation, that is why it is called a double rotation. So first I will rotate xy, okay. Let us see what will happen after I rotate xy. This is what it will look like. X has moved up, y has moved down, T1 remains the left child of y, T3 remains the right subtree of x, and T2 switches loyalties from x to y. So earlier it was the left subtree of x, now it is the right subtree of y, and T4 remains as it is. Yes, everyone with me? And I have just copied the same height. So T1 has height h plus 1, T2 has height h plus 1, T3 has height h, T4 has height h plus 1, no difference. Is this balanced? Is this height balanced? Height of y is h plus 2, yeah, because both of these have height h plus 1. Height of x will be h plus 3. Actually now there is an imbalance at x itself, yeah, because this has h plus 2 and this has h. So there is an imbalance here, and height of z would be h plus 4 because this is height h plus 3, one more, right. So this rotation has not done the job for us yet. So we need to do one more rotation. What other rotation do I need to do? Rotation xz. Yeah. So what will happen now? X will go up and z will come down. X will become the parent of z. T4 was the right subtree of z, so it will remain the right subtree. Y had T1 and T2 as its left, they will remain as they are. And T3, which was the right subtree of x, now becomes the left subtree of z. The same thing. Yeah. Okay. Now let's compute heights. Height of y, h plus 2. Height of z, h plus 2. Height of x, h plus 3. Height balance happens. Yeah, this is balanced here, it's balanced here, height is balanced here. Furthermore, the height of this subtree is the same as the height of the original subtree we had, h plus 3. Right. So final tree has the same height as original tree, hence we need not go further up the tree. Everyone follows what's happening. You understand the need for a double rotation here. Right. We ended up doing the same thing. As I said, the middle key ended up being at the top, because we want to be able to split the thing uniformly now. Yeah. Why was the height here why was the height imbalance happening? Because this was the middle key, it was coming way down, right? Now when I kind of split uniformly, the heights reduce and there is a height balance. That's roughly what is happening here. How much time does a double rotation take? Constant time. Yeah. Okay, everyone with me? So just as a quick recap, we have 4 different ways to rotate nodes in an AVL tree. So the single rotations were something like this, right? They were all in a line, x, y and z, or they were like this, x, y and z, right? And after rotation, this is the picture you get, and here after rotation, this is the picture you get, right? This is just as a recap. You understood why we are doing this thing and why this picture is a balanced picture, a height balanced picture. And we also saw double rotations. So either like this, in which case after rotation you got something like this, and or it could be like this, left and right, in which case again after rotation you got something like that. Yeah, this is just to show you the picture. You don't have to understand much here. You have hopefully understood why the single and double rotations are done in the way they are done. Okay, so now let's come to deletion, because exactly the same principles are going to be used for deletion also.
The rotation always converts the tree into binary tree.
It is a binary tree.
The difference exactly 2. When the difference becomes 0 between 2. The height becomes 0.
The difference between the height, does it become 0? We saw that, right? Did we see that? Let's see. Here it became 0 at this node, but not at this node. Here the difference, here it is 0, but at this node the difference is a 1. Right? On some nodes there would be a difference of a 1, some other nodes there would be a difference of a 0. Okay, so now let's look at deletion. So in a binary search tree, when I delete a node, we had 3 cases, if you remember, right? When I am deleting a node which is a leaf, or I am deleting a node which has only one child, or I am deleting a node which has 2 children. When I delete a node which has 2 children, what did I do? I went to the successor of that node. I copied the content of the successor into that node and I deleted the successor. So the actual node I deleted was the successor node, and the successor node has only one child or no children. Why does the successor have only one child?
It has at most one child.
Because it does not have a left child, because if it had a left child then it would not be the successor. So it has only one child or it has no children. So the actual node that you end up deleting is either a leaf node or a node with only one child, right? Everyone agrees? This is the actual node that you ended up deleting. Okay, now what is a node which has only one child? In an AVL tree, if I tell you here is a node which has only one child, what can you say about that node?
The child is
This is a node with only one child, right? Can it have another child? Can this node have a child? No. If it had a child like this, then what would be the problem? There would be a height imbalance here. So it cannot have this child or it cannot have this child. So which means this node is a leaf. Exactly. So if in an AVL tree a node has only one child, then the child is a leaf. So if in an AVL tree, if a node has only one child, then that child is a leaf. Yeah. So what are we saying? I am either deleting a leaf. When I am deleting in an AVL tree, I am either deleting a leaf or I am deleting the parent of a leaf. If I am deleting a node with only one child, then it is the parent of a leaf. Yes. So which means that I am essentially deleting a leaf. If I am deleting the parent of a leaf, then essentially, what am I doing? I can think of it as if I was deleting the leaf and copying the content of the leaf into the parent. So I can always think of it as if I am deleting a leaf. Yeah. So I am either deleting a leaf or a parent. Let's just keep that in mind. Okay. So let's say W is the node that we are deleting. Okay. Now we are going to define our x, y and z slightly differently, right. So Z is once again the first unbalanced node that we encounter as we go up from W towards the root. Right. When I deleted W, once again what is going to happen? The ancestors of W, their height could reduce, right. So on one of these ancestors will be unbalanced. If any are unbalanced, then one of these will be unbalanced. So let's say Z is the first unbalanced node encountered while we are traveling up the tree from W. Okay. Now Y is not the child of Z on the path, but we are defining Y as the child of Z with larger height, and X is the child of Y with larger height. Okay. Z has two children. One of them has a larger height than the other one. Yeah. So we take that one. So once again we will perform rotations to restore the balance of the height balance of the subtree rooted at Z. Now what is going to happen here is that this rotation now we are doing. So in the case of insertion, what was happening is that once we did this rotation, we did not have to worry anymore on the ancestor nodes, right. Everything was taken care of. We could stop after doing the rotation. Now in delete, what we are going to see is that we might have to continue up, and we will see what the reason for that is, right. So you might have to continue up the tree, go to the ancestor of Z and once again find the first node which is unbalanced and repeat the rotation there, and after that go even further up, find the first node which is unbalanced, repeat the rotation there, and so on till you reach the root. Okay. So let's understand what is happening.
Okay, sir.
Yeah.
So in the previous slide,
Yes.
sir, you are saying that X is the child of Y with larger height, but Y is not imbalanced. Both the children might have the same height. You are saying
Z is the Y is the child, X is the child of Y with larger height. Yeah. If both of them have the same height, then we will say which of them should be X. We will say that in a minute, right. It could happen. So his is a valid question. Both the children of Y might have the same height. So then which is X? We will see which is X. Okay.
So the same implies for Y also.
No, the two children of Z cannot have the same height
because that is unbalanced.
because that's the imbalanced node. right? Okay. Ignore these h minus 1 or h minus 2 for a minute. They should have come at the end. So this is the picture. I have z, which is the first unbalanced node. Y is the child of z, which has larger height, and x is the child of y, which has larger height, right? And I did a deletion in T4, let's say. I did a deletion in T4. I started going up the tree. I found a z. Yeah, I found a z. Y was okay. Can y be? So valid question. Can y be this node here?
No, because height of y will decrease. It cannot increase.
It can never be the
Height of any node in the tree in which you are deleting will decrease.
Right. So the height of this, if y was here, then its height would have actually decreased, right? So so what's the problem?
So y can never
Y
be
is
on this side. It will always be on the other side.
And you're choosing y to be the larger, so it cannot be the one which has decreased.
Okay, yeah. So did everyone follow what you're saying? Let's see. So question is, why did I draw y to be this? So my w is somewhere here. The node I deleted is somewhere here, right? I said I started walking up this, and I came here, and this was the first node I identified which had an imbalance, right? And then what did I say? Let me take, so this node has two children. This is one child of z, and the other child of z is this one. I said, let us take the child of z which has larger height. Why could it not have been this node which has larger height?
Because if it is h plus 1 initially, so it has reduced to h or
Right. So this is very simple actually. There is an imbalance that happened here. Earlier there was no imbalance. Imbalance happened because this decreased. The height of this guy decreased. Yes? So if there are two things which are balanced, right? If there are two things which are balanced and one of them decreased, yes, then what can we say about the relationship between these two things initially? Could this have been smaller than this? No, because if this was smaller than this, then actually they will become more balanced now. So this must have been larger than this for imbalance to have happened, right? So this is why, therefore. Okay. So the height of T4 has reduced from h to h minus 1, let's say. What can I say about the height of y? H plus 1. Yeah? Everyone with me on this? So why? Because originally, so it's h minus 1 now, right? So this means that this must be h plus 1 or h plus 2. It cannot be h plus 2 because then originally also it was unbalanced. It cannot be h minus 3 kind of a thing because then initially it was unbalanced. So it has to be h plus 1. So height of y is h plus 1. Okay, now x is the two of the two of these, x is the one which has larger height. So what is the height of? So height of x is h. Yeah. What can I say about the height of T3?
it can be h
or h minus 1.
It can be h. So since this is y is balanced, so this can be h or h minus 1. Yeah, because y is balanced. Okay. Good. I'll take these y, these are this in the next slide, right. So this is what we have argued so far. This goes from h to h minus 1, this is h plus 2, this is h plus 1, h or h minus 1, right. So this is height is h, so one of them, and this is also balanced, right? So the heights of these two are h minus 1 or h minus 2.
Only one can have.
One can.
H minus 1,
Only one can have.
1 has to have a height of h minus 1. So both cannot have a height of h minus 2. That's the only thing we can say. Both can have a height of h minus 1. So you can't say that only one can have a height of h minus 1. That's a wrong statement. At least one has a height of h minus 1. So let's do a rotation now to see what needs to be done. So these are the various heights that we have seen. Yes? This is what we argued in on the last two slides. Okay, now what kind of a rotation should I do? I'll do a rotation YZ once again. Yeah, similar to what I did in my insertion. So as a consequence, you'll have this kind of a picture now. Yes, Y went up, Z went down, T4 and T3 became the two children of Z, and T1 and T2 are the children of X. I have written down the heights, h minus 1 or h minus 2, h minus 1 or h minus 2, h or h minus 1, and h minus 1. Yeah, because T4 went from h to h minus 1, so this is h minus 1. What is the height of X now? This is h minus 1 or h minus 2, this is h minus 1 or h minus 2, but one of them is at least h minus 1. So X is h. What is height of Z?
H or H plus 1.
H or h plus 1. So what is the height of Y? H plus 1 or h plus 2. What was the original height of this tree? H plus 2. So if this is h plus 2, then we are okay. We don't have to continue. But if this is h plus 1, then we may have to continue, because this now becomes the bigger tree. देखिए जैसे मैंने यहाँ पे माना कि इसकी हाइट h to h minus 1 गई थी, अब इस पूरे की हाइट h plus 2 to h plus 1 गई होगी. तो we will have to continue the argument as we go up. Everyone follows this? Yeah? The way we said iski height has reduced from h to h minus 1, now we might have to say that this bigger thing ki height has reduced from h plus 2 to h plus 1, and we'll have to repeat the argument at the next higher level and so on. Good. So after rotation, height of subtree might be 1 less than original height. In that case, we have to continue up the tree. Might be, you understand might, yeah? Because it could not have reduced, in which case we can just stop. So this is single rotation in the case when this was the picture. Y was a left child of Z and X was a left child of Y. But we could have this kind of a picture, that X is a right child of Y. Yes? So the first part of the argument is the same. This has gone from h to h minus 1. So we argued that the height of Y is, what was it? H plus 1. So height of Y is h plus 1 and height of X is h, because X is the one which has larger height, and height of Z is h plus 2 because height of Y is h plus 1. Yeah, and this is height h or h minus 1. Good. Now how about the height of T1? So Y is balanced, so height of T1 is either h or h minus 1. Now if height of T1 was h, then what I would do is I would pick the root of T1 as x. Right? So it will, in that case I will be able to do that single rotation of mine, the previous case. If the height of this is x and the of this is h and the height of this is also h, right? The same thing, the question that he had asked earlier, then which do we pick? Now which one will I pick? I will pick the one which will give me the single rotation case, right? I can't say I'll pick the left child or the right child. I'll pick the left child if Y is a left child of Z. If Y were a right child of Z, then I'll pick the right child. Yeah. So therefore, since such was not the case, height of T1, if it were h, then I would have picked x as the root of T1. So height of T1 is h minus 1. Height of T1 is h minus 1. Yeah, and since the height of this is h, these are the same as before, h minus 1 or h minus 2 for both of them, with one of them at least being h minus 1. So this is a new picture now. Okay. So let me just copy it here. These are what the heights of the various nodes and trees are. Okay. Now let's do the double rotation step. So first I am going to rotate as before x, y. The same process as an insertion essentially. So with the rotation of x, y will come down, x will move up. I would get such a picture. T3 is the right child of x now. T1 and T2 are the two children of y, left and the right subtrees of y. This is h minus 1, this is h minus 1 or h minus 2, this is h minus 1 or h minus 2, this is h minus 1. Okay. Now what are the heights of these nodes? Height of y is h. What about height of x? H plus 1. And there could be an imbalance at x if this were h minus 2. And height of z is h plus 2 because this is h plus 1. And there is an imbalance at this node. So there could be here, there is here, there is none here. Yeah, but we are not done. So we'll now do a rotation around xz. Yes, and now what would happen? X moves up, z moves down, T3 and T4 become the two children of z. T3 has height h minus 1 or h minus 2, T4 has height h minus 1. This is the height of T4 and this is the height of T3. This is the height of T2, h minus 1 or h minus 2, T1 की height h minus 1 है. What about the height of y now? H. Is it balanced? Yes. This is h minus 1, this is h minus 1 or h minus 2. What is the height of z? H. Is it balanced? Yes. H minus 1 and h minus 1 or h minus 2. What is the height of x now? H plus 1. It is also balanced. But this height is now strictly 1 less than this. तो इस केस में तो आपको move करना ही पड़ेगा. There is no might this time. Yeah. Okay. Why did I make that argument कि इसकी height h minus 1 है ना कि h? हाँ, we could have done single rotation, but मैंने वो मुझे क्यों invoke करना पड़ा कि single rotation कर लेंगे and all that thing. अगर यहाँ पे अगर ये h होता तो देखिए क्या गड़बड़ हो जाती. T1 की हाइट h plus 1. अब ये this can be imbalanced. अगर ये h minus 2 है तो ये h है और ये h minus 2 है, तो इतनी मेहनत करी मैंने और कोई काम नहीं हुआ. राइट, यहीं पे इम्बैलेंस अभी भी रह गया. तो इसके लिए आई रिक्वायर कि ये हाइट h नहीं हो सकती. और कैसे नहीं हो सकती, इसके लिए मैंने क्या आर्ग्यूमेंट निकाला कि अगर इसकी हाइट h है तो हम सिंगल रोटेशन वाले केस में चले जाएंगे. तो हम उसको इसके रूट को x पिक करेंगे. यू अंडरस्टैंड वाई आई हैड टू मेक दिस काइंड ऑफ एन आर्ग्यूमेंट. वाई डिड आई हैव टू से कि इसकी हाइट h नहीं है. Good. So hopefully you all understand this. Any questions? Right. So what has happened is final tree has height less than original tree. We need to continue up the tree. Right. You understand the need for continuing up the tree because the height has reduced by 1. As a consequence, there could still be imbalance at the ancestors of this now whatever is this node in Kansas.
I think the next one will suffice. Means after the first ancestor of Z, checking at that one will
No.
If there does not occur an imbalance on the next one,
Yeah,
then it won't occur anywhere up the tree.
that's not clear.
So suppose there is an Z1 is the parent of Z.
Right.
If there does not occur an imbalance because of this
Right.
decrease in height,
Yeah.
then it won't occur anywhere above.
Why?
He's right.
That is definitely the case we are already only a deletion with the node height imbalance is created. In this case,
Okay, this will require a proof even if it is correct, right? So think about it. It's a good question. He is asking me if whether we can just be satisfied by checking the parent of this node, right. So think about this and we'll answer it maybe in the next class, maybe after the class. Okay, so let's quickly look at what the running time of insert and delete are. Okay, so for insertion, we spent login time in finding where to insert. Why login? Height of the tree. We actually spent time proportional to the height of the tree, which is the height we argued in the last class is login. So we spent login time coming down. Then we spent login time maybe moving up, at most login, right, because that's the height. And then we spent constant time in doing a rotation, and one rotation and we are done. So the entire thing is only login. And in deletion, recall that in insertion what we said was that you will first find the node in the binary search tree where the insertion has to be done. You will insert the node, then you will start moving up the tree to find the place where the imbalance occurs, the first place. And then at that place we said we will just do a rotation, and with one rotation you will be able to satisfy the height balance property once again. So insertion basically requires order login time to insert the node, and you might have to spend order login time to move up and a constant time to do the rotation. So in all it just takes order login time. Deletion on the other hand also requires only order login time, but we need to do a little bit more work, right. The reason for that is that to delete a node, recall that you have to identify which of those three cases the node is in, as in whether the node you are deleting is a leaf node, or if it has only one child, or if it has two children, then we need to find the successor of the node. So we need to go right and keep going left, find the successor, swap contents, and then delete the successor node. Once you delete it, now you have to move up the tree to find the first place where imbalance occurs. Having found that, you do a rotation. That rotation may or may not solve your problem. If it does not solve the problem of height balance, it does not restore height balance, then you might have to continue up from that node, right, and maybe once again perform a rotation. If that solves the problem, then you stop, otherwise you will have to continue up. So in all, the number of rotations you might require is as large as the height of the tree, right, because with every rotation you are moving one level up. So you might require as many as order log n rotations, but each of those rotations is only taking a constant time. So the total time required for all these rotations put together is only order log n, and we took order log n time to delete the node. All the rotations also took order log n time, and so the total time required for the entire delete operation is still order log n, right. So with that we will end today's class. We saw how to do insertion and deletion in AVL trees, and we argued eventually that the total time taken for both insertion and deletion is only order log n. Yeah. In the last class we had seen that the time taken for search is also only order log n in the case of an AVL tree. So all the three operations of insert, search and delete can be done in log n time in a AVL tree. Thank you.